Aaron, at Neptune Nanotechnologies, you're pioneering breakthroughs in materials science. What was your inspiration for identifying the chitin nanocrystal and its promising properties for materials science?
I like seafood. That's straight up the answer. I love seafood, especially crab legs. But the biggest thing I hated was how difficult it is to crack open.
Right.
After that fumbling with the crab leg, it came to me that there has to be something inside these shells that's both incredibly strong and biodegradable at the same time, because they're just shells. So of course, I did my research, did my digging, and of course, I don't want to take credit for inventing the nanocrystal because it naturally existed inside the shells. And there were a good amount of research paper publications on the topic already, and at Neptune, we are simply among the first to commercialize the process.
The process of extracting them.
Process of extracting it. These tiny little shards of crystals are embedded inside crab shells, but they're embedded within a material that's identical to it. So effectively, you're not even finding a needle in a haystack, you're finding a needle inside a big pile of needles.
Right.
So we do have to go through multiple iterations, inventing our technology, and to get it to the state of where we are. And of course, we have several patents filed on the topic.
So Aaron, what are you excited about as the application in the pulp and paper example?
Actually, a discovery that was made in the lab almost by accident. We're just playing around with what can we add the nanocrystals to, and we had a Tim Hortons tray lying around, and so we decided, why don't we add a little bit of the nanocrystals into it? And what we got is we actually got more than doubling of the strength. So if you imagine what we can do with this, right? Imagine all the shipping boxes you see going around the world. Imagine all the packaging. By doubling the strength, we can actually reduce the packaging weight by half and still maintain the same strength properties. So that's number one. Imagine all the ESG savings from all the shipping and all the carbon reduction we can do. That's number one. And number two, if we think about pulp and paper, we think weak, disposable products. But because of the newfound strength, it can actually be made into durable products. What's great with that is, of course, we don't want to be
multiple use.
Multiple use, exactly. Right. So that's number two. And number three, we know pulp and paper is actually biodegradable and recyclable. But what most people don't tend to know is there's a limited life cycle that you can recycle pulp and paper. The reason that happens is because pulp and paper is natural wood fiber, and every time it gets recycled, it gets basically chopped down into pulp. All the fiber get chopped down.
Weaker and weaker.
Weaker and weaker, right. Eventually to the point that it becomes unusable. Effectively, by adding strength, we're adding additional recycling life cycles to it. So these are the most exciting aspects that we see.
So Aaron, in that pulp and paper and packaging example, what exactly would be the cost benefits and performance enhancements?
If you think about it, we add less than 1%. That's number one. And number two, you may think that nanomaterial must be exceedingly expensive, but what's extremely unique about chitin in general, and our process specifically, is chitin is actually a waste source. Just in Nova Scotia, we dump like 500,000 tons of these shells back into the ocean a year. They're fine, they're biodegradable, but it's a source that we're not effectively using. So our feedstock is really cheap. We get our nanomaterials out of it, and then the residual, there's additional value that we can get out of it. There is.
Oh, so you're selling that back into the marketplace.
We're effectively selling that back into the industry because there is another chemical that you can extract out of these shells called chitosan. It is an antimicrobial agent that's used in cosmetics. So effectively, by having low-cost supply, scalable process, and recovering nearly all of our waste, we can keep our costs relatively low, and plus we're only adding 1%, and we're more than doubling the strength, which what they can do is they can really simplify and cut down their other material costs as well.
So the chitin nanocrystal, compared to other very promising new materials like graphene, for example, that are illustrating similar benefits of adding strength, reducing permeability, and so on, would that compare to a chitin nanocrystal?
It compares actually very well. So if you look at graphene, which is a hugely hot topic, how do we effectively disperse it, and having it play well with the host material is always challenging. So you can't never fully extract the full strength out of it. That's number one. And number two, the highest value proposition for graphene is actually the electrical conductivity type of properties. So you see it more in batteries and energy storage rather than just a strength enhancing agent. That's number two. And number three, graphene is fantastic, but it's not biodegradable.
On the topic of improving other materials, epoxies, plastics, how do you see the roadmap for the chitin nanocrystal?
Epoxy is actually our next target, quite simply because it is technically easier to achieve. What we're able to do is we can actually create concentrates. We effectively preload the nanocrystal into a concentrated epoxy liquid, and then the manufacturers can take this concentrate and mix into their process.